And Dijkstra came up with this naming nomenclature. So the implementation of semaphores. This idea is all well and good, but we still need some way to come up with mutual exclusion. Believe it or not, you can actually do this with just loads and stores. And we're going to be talking about that a little bit later in class. But it's really pretty slow. And there are some algorithms that can do this with just loads and stores. But from an implementation perspective, people typically try to go faster. So if you want to go faster, it might be helpful for your computer architecture or your instruction set architect to come up with a special instruction which will allow you to do something atomically. So when we say do something atomically, it means that there's nothing else can be interleaved in the meantime. And the simple solution here is that you add an atomic operation which can do a read, a modify, and a write, all atomically with nothing else interleaving it. So going back to our locks and semaphores here, all inside of this P and all inside this V here, you need to somehow atomically modify S. You need to be able to read S. You need to be able to write S if you were to implement this somehow with code inside of the implementation of P and the implementation of V. So the primitive here that makes this faster is having some read, modify, write operation. And we're going to look at a couple different choices of this. One of the most basic ones is test and set. x86 has this instruction. This is one of the most basic operations on x86 for atomic operations. Lots of other architectures have an instruction which does this. So we write it here as a piece of code, but in reality, this is a piece of pseudocode, but in reality, this is an instruction which will actually do this atomically relative to the whole rest of the system. So let's look at what test and set does. The basic idea of test and set is it's probably one of the most primitive atomic operations you can do. I've seen something slightly simpler than this. There's like a test and clear, which is a little bit easier to implement. But largely, the idea is that you're going to look at a memory address. And if that memory address is what you expect it to be, then write some value. And implicit in this piece of code here is that the piece of code which executes the test and set needs to know whether it succeeded and was able to successfully write the value or did not write the value. So there's sort of a status code, and that's returned in this register R here. So if we look at this piece of code, you pass into it a memory reference, a memory address, which is the address of the semaphore or the address of the lock, and you pass into it and a register name. We do a load into that register, and that happens unconditionally. This part here, though, is the test part. So the test part here is we check whether the thing we just read from this memory address is 0. And if so, we're going to write a 1 to the memory address. Sometimes these test and set operations will actually allow you to write something else besides just 1. But for right now, this is sort of the more basic one here. So it writes a 1 to that memory address. And what's important here is the architecture guarantees that all of this happens atomically. But what's interesting is if you think about our processors that we've built, this requires a load and a store. So we will talk about how we implement this a little bit in a few slides. But you basically have to stop everything else, stop all other loads and stores happening in the system, do this load, do the test, and possibly do this store in hardware. One of the more basic ways that this is done, or one of the original ways this was done actually on some of the x86-based architectures, is there was something called the lock bit on the bus. So what they did is when one processor was going to go execute a atomic operation like this, a test and set, for instance, it would actually broadcast all the other processors in the system saying, I'm about to do this, do not touch anything, do not issue any memory instructions effectively, or do not issue any bus-based memory instructions. It would do the load, it would do the test, and it would do the set, and then it would release this broadcast bit. It was just a wire on a multi-drop bus. That's a pretty big hammer. Things have gotten a little bit better since then, but let's give you an idea of a basic hardware implementation of this. Things got a little bit more sophisticated. This sort of showed up in the 70s here. These fancier operations, fancier atomic operations. So this whole box here is still a atomic operation. All of the code in here happens atomically. And what this basically does is it's going to take a memory address and add something to it. So we're going to add RV to R and put that into memory at the same memory address. And so we're going to do a load and a store here atomically. So it's a read, modify, write operation also. And having it all be atomic. Note this still actually returns into register R here the original value. And sometimes that's actually very useful if you're trying to implement a semaphore based on this. You kind of want to see what was there before. There's some jokes around fetch and add here, though. The atomic operation community kind of pushed this to the extreme at some point, and people started having sort of fetch and insert something here. So fetch and multiply, fetch and divide, or things like that. And people started building some stranger machines that had fetch and something else. And there's this old joke that someone was going to implement an instruction called fetch and FFT. So it would be an atomic Fourier transform. I don't think it ever got to that point, but in the microcode days and in the early multiprocessor microcode days, there were some pretty sophisticated atomic operations. That's largely been decided to not be a good direction to go. You want to have a little bit of complexity in your atomic operations. So maybe test and set is a little too simple, but some of these fancier fetch and FFTs is probably a little bit too complex. Here's another interesting operation that is atomic. And this one you can actually build some pretty interesting semaphores out of. It's called swap. So it takes a register value and a memory location, and it will take what's in the memory location, what's in the register, and swap the two things. And note, we need to use we use a temporary here because you can't actually swap two things without a temporary. This is actually not very common because it's kind of hard to use. Something's a little bit more common is something called compare and swap, which is something between kind of a test and set and a swap operation. And that's what's commonly used. We'll talk about that in a second. OK, so now we go back to the multiple consumers problem that we had where multiple people were trying to dequeue from a queue. And let's introduce test and set. And we'll look at our critical section here. We're going to use this term mutex to basically mean a semaphore that only one thing can enter at a time. So what happens at the beginning here is there's a tight loop. And this tight loop will read from the memory location of mutex into a temporary register, and we'll compare it to 0. Note, we define test and set as writing 1 to memory if it succeeds. So if it was 0, that means that it was not able to actually modify memory. The test failed. So if the test failed, it's just going to spin here. And we'll call this busy waiting or spin, traditional spin lock, it's called. If it acquired the lock, this read value would have been a 1. So it would not be equal to, or excuse me, if it acquired the lock, let me do this right. if it's 1, if it's 0. OK, sorry, we did this wrong. If the memory address was a if it was a 1 coming into here, that means someone else already locked it. If it's a 0 coming into here, that means no one locked it, but we locked it and set it to a 1 now. So if we acquire the lock, we're going to atomically set it to a 1, and we're going to read a 0. So we'll drop into our critical section and start executing our critical section. And under the critical section, we can do stores, we can do loads, we can do whatever we want, because we're guaranteeing that no other processor or no other thread is doing anything to it. And then at some point, we need to do the release here. And that we actually don't need a test and set for. We just need a store. The store is just going to clear that memory location, and some other thread is safe to go and fall into the critical section here. OK, so this can be done with lots of different implementations. We showed here of test and set, but this can be done with swap. It can be done with fetch and add. The code gets a little bit more complex. But one of the interesting questions that comes up is, what happens if you're running along, some thread acquires the lock, falls into the critical section, and let's say terminates, or gets swapped out for a very long period of time? What's going to happen here? Well, system crash. I mean, we don't reference bad memory here. This is more of a hang. So it's going to freeze. So this is actually pretty common in the old, for instance, if you look at like non-preemptive operating systems. So back in the day of like the original Mac OS, before Mac OS became Mac OS X, so versions sort of 9 and earlier, that was a cooperative operating system. And if someone went and grabbed a lock and then died or took an error case, the whole machine would crash. If you're preemptive, I mean, there's like a timer interrupt going off, it's possible you still won't be able to make forward progress. But at least the OS can interrupt your process and try to do something about it. It can detect that one process is hung. But in a cooperative multi-threading environment, if one process, let's say, just hogs the processor and never gives back the processor or just dies, and you have some other process or let's say you grab the lock in one process and die, and then another process is running along and tries to acquire the lock, but it's just sitting there spinning in this little spin section here for forever, you're basically just going to hang the processor. You're just not going to see anything else happen here. So you got to be pretty careful, especially in cooperative multi-threading environments. So one of the tricks to this, actually, is if you're in a cooperative multi-threading environment, you'll typically put inside the spin loop here something which will yield to a different thread. So someone else can try to do something in that time. Because if you just sit there spinning, it's very possible that you won't be fair, or no one else can ever go to unlock the lock, for instance. So you got to be a little bit careful there. OK, so we're going to move forward here and look at how to do a slightly different version of the same piece of code, but now with compare and swap. So before we do that, let's talk about the semantics of compare and swap. Compare and swap takes memory and 2 registers here, and it's going to compare memory with one of the registers. If it's equal, then it's going to take the other register, put it in memory, and effectively swap them and return a status. If the compare operation fails, we come to this else statement here, and we don't do any swap. So this would be effectively taking a register and a memory location and swapping them, dependent on another register. So it's a little bit more powerful than just swap. It's a little bit harder to implement, as you might imagine. It's probably not as hard to implement as something like fetch and add. And the reason for this is, if you want to go do this operation out at the memory system, you can basically send it as an atomic sort of operation. Go to main memory, compare this, put a comparator there, and swap the two things. If you try to have these sort of increments or arbitrary instructions or adds, you need to put an adder out there for sure. This only needs a comparator out there. Still painful to go implement, but it might be a little bit better than putting a full adder in your memory controller, because that's almost like duplicating your ALU out in your memory subsystem, which doesn't make a whole lot of sense, but that's why people used to joke about the fetch and FFT. But OK, so let's take a look at the same piece of the same case here of a multi-reader piece of code, but instead what we're going to do is we're not going to have a spin lock at the beginning. Instead, we're going to have a critical section, but we're going to concurrently execute critical sections from different threads here, which we're not going to call it a critical section then. We're going to say we're going to concurrently execute what was in the other thread's critical section, and then we're going to atomically try to swap out the head pointer and replace it. So we're effectively doing speculative work here. And this is called non-blocking synchronization. So the synchronization primitive, we're going to do the loads. We talked about that before. We check to make sure if there's at least something available. We pull the head pointer off. This is all speculative work at this point, because we have not checked to make sure that we can validly pull off the head of the queue. We're going to increment the head pointer into a temporary here that we're going to call new head or register new head. And then we're going to try to swap the new head with the old head atomically. So it's going to take the register that we think is the new head and the memory location where the head pointer is. We're going to try to swap these two things. And the thing that we're dependent on here is whether what we think is the old head still is the old head. And if something bad happens here, we can try again. So the idea here is that we're going to spin actually in this effectively bigger loop, trying to speculatively try to go and change the head. So one question that comes up here is, what if the head was dequeued from, added back onto, and it just so happens we have some sort of, it's called an ABA problem. The head pointer was A, it was changed to B, and later was changed back to A, all in this short period of time. Yeah, that might be a problem here in this piece of code. You might need to think about that and carefully reason about that. Usually you can protect that in some other way, sort of when the pointer wraps around maybe. If you think about a normal array, when it wraps around, you put something which is not a compare and swap. You put it like a more spin lock or a spin loop sort of lock on it. So you only have to worry about that in these sort of circular buffers when something wraps around, because otherwise there's no other way that the head pointer can go back to where it was before. But you do need to worry about that you wrapped all the way around the array in this very short period of time. So there's some race conditions that happen with these non-blocking synchronization operations. Another non-blocking synchronization primitive that is actually really cool, I think, goes by lots of different names. It goes by load locked, load linked, load reserve, and store conditional. So you take your ISA, you take your instruction set, and you add two new instructions. something which checks to make sure, or something which does a load, and what you then do is store conditional checks to make sure that no one else did a load or a special load link to that same address in the intermeeting time. I can explain that one more time because that's a little confusing. But the basic idea is there's a flag register here. And in hardware, you do a load link. This loads the value into your register. And sort of on the side, somewhere next to the register, it may not be architecturally visible, or shouldn't be architecturally visible likely, it'll set a bit. You execute your critical section, and when you come back to it to go do the store, we'll say, for these sort of read, modify, write operations, when you go to do the store checks to make sure the flag is still set to 1. If flag is 1. If it's still 1, that means no one did any memory operations to that address, or did at least any load links or store conditionals to that address in the intermeeting time. Actually, sorry, we'll say that more concretely. No one else did a store conditional during that time. So no one else tried to do a store update. Other people might have tried to do a load. But no one else did a store to that address, or a store conditional to that address. Because if someone else did a store conditional, what will happen is it'll actually cancel the other processor's reservations. So it'll set their flag bits to 0 atomically. This is a pretty primitive. This is a pretty powerful primitive here, such that you can basically do a load, try to do a store later in the future. If no one else tried to do a store to that same address in the meantime, or a store conditional to that address in the meantime, your store goes through, and everyone else's loads, if they did a load in the meantime, would get invalidated. Or they'll know that it gets invalidated when they go to do a store conditional. So if we take the same example here and we implement it with load link and store conditional, we're going to look at the head pointer here where we normally do the update, and we're going to do a load into this register. And when we go to do a store conditional, if someone else had changed this value in the meantime, we're going to get a fail, and we're going to jump back around and have to redo the load link. And this actually gets rid of the ABA problem also, because if you did have that sort of race, someone else would have done a store conditional to that address, and the wraparound cases and all that stuff would actually, and it would invalidate your flag on that bit, if you will, or flag on that memory address. One of the reasons that people like this is when you go to do load link or load reserve and store conditional, you can a lot of times sort of piggyback this over a memory coherence protocol, such that you do a load link and it'll add an extra bit in your memory, we'll say. So if you're doing some sort of memory coherence protocol, it'll pull it into your cache, and you can sort of tag this line as special, or that's the flag bit here effectively. You can say this whole line was load linked. And then if no one else pushes it out of your cache or fetches it from your cache in the meantime, this would mean no one else did a load link on it. By the time you go to do the store, you know that no one did anything. And what's really nice about this is there's no communication that has to happen between the processors on the common case with an uncontended lock. Versus the spin locks are generating memory traffic all the time. They're sitting there doing loads, doing stores, trying to like grab the lock, trying to grab the lock, trying to grab the lock, and they're just generating all this traffic all over the place. Versus this is very quiet. You just pull it into your local cache, and if by the time that you get back to it, it was still in your cache and it still has this bit set, that's great. You get to do it. In the contended case, though, you might actually get traffic ping-ponging here, but you can still guarantee correctness. So this brings us to performance. As I said, some of these blocking atomic operations can generate a lot of memory traffic. So they'll just sit there spinning on memory, and they'll at least be doing lots of loads. And those lots of loads might be going out to main memory. Non-blocking atomic operations, so like these compare and swap operations, or load linked, store conditional, and the load linked and store conditional, as I was alluding to, many times you can do it against your own cache. Also, these things can sometimes have better performance because you don't have to sit there sort of spinning in tight loops. You can try to do stuff in the meantime. The downside to at least the compare and swap implementation is you have to do sort of speculative work in the meantime. You're sitting there redoing some work, and if you didn't get the lock, that performance can be bad. There's also, as I alluded to at the beginning of class, there are things that use ordinary loads and stores, or algorithms that do implement locking with just loads and stores. Their performance is not very good. And we're going to look at an example of that called Decker's algorithm today. Finally, the performance of these isn't just dependent on the operations themselves. Some of these primitives, hardware primitives, have better performance or worse performance depending on how highly they are contended. So what I mean by contended is I mean you have multiple threads trying to acquire the lock at the same time. If you have lots of people trying to fight for the lock, that's high contention. If you have a lock which there's almost never contention on, you just go to get the lock and you just get it, and it's there for a really rare case, other locking primitives have better protocols there. And of course, we're going to talk about this in a little bit of how do you make these integrate well with caches, out-of-order processors, and out-of-order memory systems.